All right, let's get started. Welcome to the session on core software design principles for programmers. My name is Venkat Subramaniam. We're going to talk about some design principles and things that can help us a great deal when it comes to developing software. Best time to ask questions is whenever you have it, so please don't hesitate. We'd love to hear your questions or thoughts if you have any. So I want to talk about some design principles, but before I talk about it, one of the things we do as programmers oftentimes is we get really excited about design patterns. We want to apply different design patterns. But it turns out that a lot more important than design patterns, I find these design principles to be extremely important when it comes to developing better quality software. And I've seen these principles to be valuable almost in every single day of development, especially during what I would like to call as tactical design. I'll talk more about this a little later. And so I want to spend a little bit of time talking about some of these principles that can help us not only write code, but also be able to maintain the code along the way. So where can we see these patterns being used? These patterns come into play in almost constantly in design, but I don't consider design to be a lot separate from the act of coding. They kind of work hand in hand, and the code has to evolve, and the design kind of lives in the code along the way. If somebody tells us that the code has deviated from the design, what they normally say is the code has deviated from the design document, but the design actually lives in the code, and we can definitely benefit from it. But why use them? And one of the challenges we often face is to be able to develop software that is extensible, maintainable, and to be able to understand the code and evolve it. And what are the things that really make it really hard to extend the code? One of the things that make it really hard is dependency. The more dependency we have in code, the harder it is to change the code. The other thing that makes the code really hard is when a code does way too many things than it's supposed to do. And the opportunity for the code to change increases the more it does it. But these principles kind of tell us to keep an eye on some of these issues. When do we use them? I often use these principles during test-driven development. So as I'm writing test cases, to me writing test is not a mechanical process where I write a test and just let the code run, but I would write a test and I would spend some time thinking about the quality of the code being tested or designed with this test. And this often influences based on these principles. And oftentimes, the other place where I use this quite heavily is as a vocabulary to use among developers. So oftentimes when I do code reviews or design reviews, I would often say, well, let's keep this code dry, or let's not violate the dependency inversion principle here, or open close principle. So these tend to be really useful for those. So we're going to talk about some core design principles. And I'm going to start out with one particular principle here that I find to be extremely valuable to begin with. And if there's one thing we can do, probably this is the first thing I would like to attack, is the so-called dry principle, also known as don't repeat yourself. So one of the challenges we often run into is that code, not only code, but also effort gets duplicated oftentimes. So one of the things we do naturally as programmers is, without even thinking sometimes, copy and paste code. And when we copy and paste code, we end up having the code in multiple places, and when the time comes to make a change, whether fixing a bug or making an enhancement, we got to make in multiple places. But it's not only about fixing the bugs, duplicating the code, but it's also duplication of effort. And we often tend to forget that. For example, how many times have we written software where we have a change in requirement, and as a result, we have to change some UI code, we have to change the controller, we have to change the model, we have to change the schema, and then we shrug our shoulders and say, that's life in the big city, what can we do? And we make all these changes. But that's an example of duplication of effort. Another thing that we often get ourselves convinced with is, we may say that I have to perform a validation. Well, clearly, client-side validation makes things much more faster and better, but we cannot do it in exchange for server-side validation. Well, oftentimes our server-side code may be Java or something else. Our client-side code may be JavaScript. Oh, after all, these are two different languages. We got to implement the validation in both places. Well, right there is duplication again. So we have to rethink about how we can capture this logic, the rule, in one place, and maybe code generate in other places to avoid it. So this is where the dry principle comes in. So what does the DRIVE principle say? The DRIVE principle says that every knowledge, and this is basically what we do, is we are knowledge workers, right? We represent rules and logic and knowledge in system. And so it says every knowledge in a system should have a single, so should have a single unambiguous, unambiguous, authoritative, I'm going to spell these wrong, so authoritative representation. So in a sense, what it says really is, it says when we look at a system design, every piece of knowledge in a system should have a single unambiguous authoritative representation. So when you capture details in a system, ask yourselves, what is the right place, a single place for this to exist? It reminds me of a few experiences. I was talking to a developer not too long ago, and he said that in their software system, things have been duplicated in so many places across. He said that they fix the same bugs every 2 months. I said, oh my gosh, did somebody put the bug back after you fix it? He said, no, because this code is duplicated in so many places, we keep discovering new places where this is duplicated. I asked him, how does it feel? He said, that really sucks. And then I said, when you do find this duplicated code, you take a minute to refactor and remove the duplication, right? He thought for a minute and said, that's a great idea. Well, the point is, if we never take the time to remove the duplication, there's absolutely no way to escape it. So this is not just about duplication of code, it's a duplication of effort as well, like I said, and we got to be careful about it. For example, I was talking to a team when the manager said, the team every single day promised that the software is extensible and they're building for extensibility, and don't worry, when we have to extend it, we can do it. Well, they released the product. Within 24 hours of releasing, they found out that there was a problem in one of the data being entered. They need an additional field to be entered. So when the request came to the manager, like every manager does, he promised he would have that ready for them by the next day. But of course, in this case, he did so because the team kept saying the software is extensible. So when he came to the team and said he has to make this change to add this one field into the view, the team said they need a few weeks. So he protested saying, why would you guys need a few weeks to do this? And they said that's because we got to change the database schema, we got to change these controller classes and the models, and then we got to change the UI, and we got to make all of these changes in multiple places. So he was asking me, how does this what does this mean? Because the team kept promising me that the software is extensible, and why are we having trouble with this? And I told him that the fault is his. And he said, why is it my fault? And I said, the software actually was extensible until you asked it to be extended. So this is something we all do, right? We have this theory of extensibility, and it's unshaken until somebody says, now extend it. It's like, oh dear, we can't do it after all. So one of the reasons this happens is because, again, duplication of effort, we got to do these changes in multiple different places. So if there's one thing we can do, we can try to eliminate this duplication. Not only duplication eliminated in code, but also eliminated in test cases as well. And ask the question, what is the single location where this particular logic, this particular rule or logic has to be kept and go towards it. The next principle that I like to really use, and I'm a huge fan of this particular principle, is called the Yagni principle. And Yagni principle stands for you aren't going to need it. And when I tell programmers you're not going to need it, they get pretty apprehensive. So I normally throw in the word yet after that, and that makes a world of difference. And they say, if I don't need it yet, can I do it tomorrow? Well, absolutely, let's talk about it tomorrow, and repeat the same thing. So the point behind Yagni principle is, you postpone something until you no longer can postpone it, or you don't need it anymore, and then you don't end up doing this. Now, one of the challenges we run into oftentimes in developing software is, we as programmers are excited about implementing code. That's what we do. We love writing code. But the problem is, we end up writing so much more code than we really need. And it's shocking to see that sometimes by not writing code, we can actually develop better software, much smaller software, much leaner software than by adding all these features. So one of the things to think about is, do I need to really implement this, or can I postpone it until later time? So here's a reason to think about this. Let's say for a minute, We have now versus, let's say, later. And the question is, what's the cost of doing something now versus doing something later? Let's say there's a $N for $now and $L for $later. And I'm going to say if the cost of doing it now is the same as cost of doing it later, let's say. Well, in that case, I would definitely like to postpone this, and I would not like to do this now. I want to do this later on. Now, what is the reason for it? I'm sure everybody here can accept and agree that we are smarter tomorrow than we are today. Would you agree with that? Absolutely, right? I've seen one person who did not agree. Nobody liked this person anyways. So the point really is, most of us can agree that we are better tomorrow, knowledgeable tomorrow than, smarter tomorrow than today. So we can make a decision tomorrow than do it today. That's much better. There's one other benefit we get by postponing things. By postponing things to tomorrow, we get to really focus on what's really imminent, what's necessary now, rather than having to take on all those additional things. So postpone it until you can no longer postpone it. In agile development, we talk about this as last responsible moment, and we want to be able to delay things as much as we can. Well, what if the cost of doing it now is going to be less than the cost of doing it later? Well, in that case, definitely we want to postpone. In that case, we want to probably consider doing it. What about cost of doing it now is greater than the cost of doing it later? Well, certainly we want to postpone it. But in this case, though, we have a fear that it's going to cost more later on. In that case, I would ask the question, what's the probability of having to really do this? And if the probability is relatively high, we are very sure, I would say let's get that implemented. If the probability is not that high, I would postpone it. I'll give you an example of this. I was implementing a feature about years ago, and I remember clearly that day, there are so many flexibilities I can provide for this feature. My need for that day was fairly minimum, but if I think of extensibility in the long run, there is so much more I can do. And there was a little battle in my head. Should I just get it done for what I know now, or should I really make this extensible? Well, here's the deal. I've got a product to release, and there's only so much time on the hand for us to spend time on features. So I made a very clear decision not to really go after a large amount of features in this particular area. I just implemented minimally and got it done. So that was about 2 years ago. And about 4 months ago, I had to extend that feature to add a few more flexibilities, mainly because users demand and they kept asking for these features. I better do this. So when I sat down to implement it, my mind immediately said, oh, if I had only taken the time to implement it back then 2 years ago, I wouldn't spend that time on the stinking code right now, isn't it? But then I had to tell myself, but I was able to release the software, get into production by not doing it, so it was really a wise decision. But the thing is, it only took me about an hour to refactor and get the new code implemented, but something else really came about doing it. The 2 years the system has been in production, I knew a lot more about the needs of the system than I did 2 years ago. So I was able to actually do a better implementation now than I would have years ago, and so in the end actually worked out fairly well with minimum effort to do it. So we need to have the courage to postpone things, and that's exactly what it is. It's a courage. A lot of times programmers want to implement things because they are either fearful or they are eager. How many times programmers say, I'm sorry I can't talk to you right now, I'm busy writing this code. What are you working on? I don't know, but I got to finish this, right? So we do this all the time. We got to really rush through and produce results. In a way, if you really think about it, this is very symptomatic of other things we see in the world. For example, if you go to restaurants, the amount of food restaurants actually serve is insane. There are days I would go to a restaurant and they would serve me food. I would look at the food and ask myself, is this my last meal? Why are they giving me so much food to eat all of a sudden, right? And I remember walking into a restaurant. I had just flown from an international trip, and I was absolutely hungry. I could have eaten the desk if I had to. I was that hungry. So sit down. The waiter comes over and he says, what would you like to order? And I said, I want to order that, and that. In a very straight face, he said, I'm sorry, who else is joining you for lunch? I said, there's nobody else. I'm just going to eat. And he said, all of this is for you. I said, yes, all of this is for me. He said, I'm sorry, I'm not going to serve you all that food. For a minute, I got really angry. And I said, what do you mean you won't serve me this food? I'm ordering this food, and why would you not serve me? He said, here's the deal. You ask for 2 out of the 4 items. I will serve you those 2 items. And when you're done with it, you order the other 2, and I will serve that to you, and I will not charge you for that. So I said, that's an interesting deal. Let's do it. And he serves me the food. I was able to eat half of the half he served me. He comes along and says, would you like more? Oh, thank you. And this is something I really appreciated because he could have taken the money and done this. Like, for example, in the San Francisco airport a couple of months ago. I went in and ordered a burrito, and then I said I would like to order a bag of chips, please. So they said, sure, and they gave it to me. And guess what? I finished my bag of chips and I opened the bag of burrito. Can you guess what was in it? Another bag of chips. And what a clown, right? Why can't they just tell me, you moron, it's already there on the bag of chips, burrito. And that's the whole point. We really need to ask the question, is this important to do? And same thing with code is if we have the courage to not write the code, we can do a better job focusing on the code that should be written. And that's basically what the Yagni principle emphasizes. But then I want to move on to talk about yet another principle, which is probably the one that troubles us the most. If you think about single responsibility principle, well, there are 2 things we can think about when it comes to a piece of code. And these are very important design metric, and one of them is cohesion, and the other is coupling. Now, if you think about cohesion, what is cohesion? Cohesion is a property where the features in a module, a class, a function, what have you, they are working together, and as such the module is narrow, focused, and does one thing and one thing really well. And you want the code to be very cohesive. On the other hand, you want the coupling to be a lot less, because the more you depend on, the chances of the code having to change is a lot higher. So let's think about why we want high cohesion and we want at the same time a low coupling. Well, let's think about cohesion for a minute. So when you think about cohesion, high cohesion and low coupling, well, if a code has less cohesion, it means it's doing a lot of stuff. The code is doing way too many things than it should do. Well, if a code is doing a lot of stuff, the number of times the code has to change becomes a lot more frequent. If a code is very narrow and focused and does one thing and one thing well, the number of times it has to change, the frequency of change is a lot less. While you want the software system to evolve, you want a particular module of code to not change as much. In other words, you want code to be more stable in different parts of the system. So having a high cohesion reduces the frequency of change for a piece of code. Having a low cohesion increases the frequency. Same thing with coupling. If you depend on many things, when any of those things change, you have to change your code. If you depend on fewer things, the frequency of change actually reduces as well. So it's important to really have the single responsibility so that the code can be narrow, focused, and do something well and focused on just one single area of responsibility. But we often know this is the right thing to do, but yet this is extremely hard for us to follow. One place where we see this is with long methods. So let's talk about long methods for a minute. Here's a question. What's the longest method you have seen in your experience? Yep. 300 lines. Anybody else? 3,300 lines. Anybody else? This sounds like an auction, isn't it? This is not going well. I was speaking in Belgium a couple of months ago. There were probably about 800 people in the room. I asked this question. And out of the darkness in the room came a voice. He said, 40,000 lines of code. And I asked him, do you work in hell? And it's kind of shocking, right? And then he came to speak to me after the talk, and I could see in his eyes, he was not kidding. And he is working on a system where one piece of code has 40,000 lines in it. It's kind of scary when you see this. But of course, we all can agree that long methods are a bad idea, but oftentimes we have to ask ourselves, why is that? But let's ask the question slightly a little differently. Who here thinks long methods are a great idea? We should write more long methods. Raise your hand if you think so. Not a single person, right? Usually there's one person raises the hand. I ask them why, and they say, because long methods give you better performance. And they're not entirely wrong. It was a time when long methods did give better performance, That's when Nixon was the president. A lot of things have changed since then. Better architecture, better compiler, better tools and all that. Let me ask you a different question though. Who here has seen long methods at work in your job? So notice hands begin to go up. A lot of hands went up. The others are so pained by it, they don't want to raise the hand, which is understandable, right? But here's the cognitive dissonance, right? We know it's a wrong thing to do, and yet we see long methods at work. Now, why is that? Well, I know the reason for it. You're not writing long methods because you clearly told me you will not agree to long methods. It's not a good idea. So the people who are writing long methods are at work right now making longer as we speak, right? And so we have to really find a reason why this is a bad idea. So what do you think? Why are long methods a bad idea? What's your thought? Yep. Are hard to implement, right? If they're long, that is. I hope you're saying that, right? So long methods are hard to maintain, isn't it? So hard to maintain. What else? Yep. Yeah, what does it do? Don't ask me, right? Nobody knows it. What else?
Why are there so many comments?
Yeah, oh, so many comments. Let's talk about that for a minute. Have you noticed this? In your long methods, have you noticed this symptom? You got code, and you got the code for several lines long, right? You got all these code. And then you see this wonderful comment. And then, right after this, you see a long list of code and comment again. And then list of code and comment. Have you seen this pattern? So I used to always think, why is there code comment, code comment, code comment? And I finally figured this out. The reason why you see this pattern of code and comment is the person who wrote this code is a bad programmer, but not a bad human being. So deep down, they have empathy, right? What if some clown ever looks at this code, and that is the reason why you see this, right? So many comments, there's a reason for it, because a person has empathy. Okay, what else can we think of? Oh, failure. So high failure rate, and so that's one other reason. So high failure. What else can we think of? Hard to debug. So hard to debug. Let's talk about that for a minute. You hire somebody and ask them to debug. What is their designation? Not a programmer. They're called victims, right? And you're like, why me? Why am I, having to debug this problem? It's very difficult to do this. What else can we think of? Yep. Oh, hard. Talk about that. Hard to test. The number of permutation and combination you have to write, right? Nobody survives writing the test for it. And then what do you say? Release it. If it doesn't work, the users will eventually tell you, right? So we kind of give up on testing. It's really hard to do. What else can we think of? Oh, does too much. So lacks cohesion. So lacks cohesion. But on the same token, we can also say has high coupling. The mystery doesn't come alone. The function says, why just be alone? Let's invite more things to the party. So the high cohesion as well. What else can we think of?
Dead code?
Oh, dead code. So there is dead code all over, okay? So we don't even know what all these code is doing, potentially. What else? Talk about that. Duplication and also hard to reuse. Think about these two together. You got this long method, and you look at this method and say, hey, what I need is these 7 lines in the middle. And you stand outside and look at it. That one, I can't get to it. So what do? I'll copy it and paste into another long method. My job here is done, right? So this is so much easier. So it's not only leads to duplication, it's very hard to reuse. Well, what else can we think of? I don't know about garbage collection. The whole thing is garbage. What else can we think of? Louder, please. Speak away.
Easy to see, must be short.
Oh! Okay, we'll come back to that in a minute. Yeah? What are the variables? What does it do? What is the state? You can go on, right? We can probably list another 20 of this. Yeah? Go ahead.
Shorter self-life.
Well...
As soon as I see it, I want to rewrite it.
Of the programmer usually, not the code itself, right? Sometimes. Yeah. Well, we can keep adding more things to this. But the point is this. We know long methods are so bad, and yet what do we see? Long methods. So this is really hard to understand, right? Because everyone knows this is wrong, And what do? We go back and write long methods more. So I have one last suggestion to be able to convince your developers not to write long methods. And this is the last effort, so we can make an effort. So here's the idea. You've told your colleague don't write long methods. They're not listening to you. So try this as a last resort. So go to work on Monday. Don't say a word. Just sit down and start coding. Your colleague, the one who writes long methods, comes to you and says, you're already here. How was your weekend? You could tell your friend, your colleague, how your weekend was like this. You could say, I went to the park with the kids on Saturday and went to the movies on Sunday. But don't say that. Instead say, the weekend. At 7 a.m. exactly, I took the car out of the garage, turned left, drove for another 3 kilometers, took a right turn, went round about the roundabout, stopped at the light for about 20 seconds, took a left turn, and then drove for another 3 miles, and then after that I turned left again. Just keep going like this. After a while, your colleague says, have you gone mad? You say, no, I thought I'll tell you how my weekend was if you write code. Right? The point really is, when we talk to people, we don't talk to people like that. We give them knowledge chunk. I went to the park on Saturday with the kids, went to the movie on Sundays, and your colleague may say, really, what park did you go to? No longer are they interested about the movie, they're interested in the park. Is it a family-friendly park? Where is that located? What are the facilities they have? Notice how we are getting deeper and deeper into this. So the question really is, what are we really after? Well, we don't want long methods. So the obvious question is, what is long? And of course, we had a little competition here. Somebody said 300 lines, somebody begged it to 3,300 lines, and we can keep working on it. But the question is, how long is long? So I'm going to say 50 lines is okay. What do you think? No, too long. Okay, what about, we can do binary search, 25. Somebody says too long, right? You could say 7, and the closure guys are laughing, right? It's like 7, that's too long. So the question is, how long is really too long? Let's try something else. We could say a function is not long enough if you can fit the entire function in a window. And the minute you say it, somebody says, really, what's the font size? So there is absolutely no way to win that either. So the problem here is, we are going at this wrong. A long method is not about the number of lines of code at all, in effect. So how do we really deal with it? My suggestion is, go for a slap. No, don't hurt your colleagues. This stands for single level of abstraction principle. So a single level of abstraction principle is really what we are after when we talk about long methods. In other words, you want every method to have a single level of abstraction. For example, how was your weekend? I went to the movies on Sunday, and I went to the park on Saturday. Well, look at the level of abstraction here. You're not giving more fine-grained details about each one of them. You're staying at that level of abstraction. That's exactly what we want to do when we write code, is we want to keep the code in a single level of abstraction. So when you look at a piece of code, rather than counting the number of lines of code you have, ask the question, what is the main level of abstraction this code needs to deal with? Are all the code really dealing with that level of abstraction? Or does any code go into much more detailed level, which means we got to extract it out to another method? And that's what we really want to focus on, is a single level of abstraction that we can provide. This would lead to what is called a compose method pattern, where a function would be simply composed of these other methods, and we can then say, if you want to know more details about this other method, you can go back and read it. Well, there are some benefits of this. The first benefit is, when you look at a piece of code, you are focusing on that level of abstraction, you're able to quickly grasp the intention or the purpose of this code. And also, if you've seen a more detailed code a little earlier, you tend to remember these knowledge chunks, or there's two options that happen. One is, I've seen that method before, I don't need to see it again in this context. The other benefit you get is, while I'm considering this operation, I can abstract out the detail. I don't need to dig into that right now. I'm going to keep my focus on this level of abstraction. So working with the code becomes a lot easier when we focus on the single level of abstraction. That is something we would definitely want to work towards. So if there are two things we can do in our industry, we can make a remarkable difference in our field. And one is remove duplication, and the other is keeping the single responsibility of code. And we don't ask this enough. We need to ask the question, what is the main responsibility of this function? And if we were to ask that question, oftentimes already we are doing better. If you ask what is the purpose of this function and somebody says it does this and, well, right there is the giveaway, the word and. It's trying to do one too many things. Let's focus on just one thing this function has to do. Same thing with classes and components as well. Well, given this, let's move over to one of the other principles I value a lot, which is called the open-closed principle. Well, Bertrand Meyer created this principle, and the principle says a software module, so this is, what is a module? A class, a function, just about anything you want to. A software module must be open for extension, but closed from modification. Now, this appears like a magic. How can you keep a module of code open for extension, but closed from modification? Well, it essentially says when you write a piece of code, if you want to extend the piece of code, you should be able to do that without actually having to modify the code. Now, why should we care about this principle? And the reason is actually fairly simple. You can all agree, I'm hoping, that you would, so here's the way to think about it, right? Let me pose this as a question. Given two choices, choice one, you got to write a little bit of new code. Choice number two, you got to open up existing code and change it. Which of these two options would you prefer? Option one, where you write a little bit of code, or option two, where you change existing code? I heard people raise the hand as one, right? Absolutely. We would rather write a little bit of code than change existing code. Now, what is the reason for it? The first problem is, the minute you open a piece of code, what happens? What happens immediately is cursing happens, right? I mean, let's be honest about it. I'm a very polite guy. I don't really speak wrong most of the time. But my wife will come to me and say, I don't understand this about you, Venkat. You are the most pleasant person I ever know. You never speak bad. But I ever come to your room when you're coding, you curse so much. How can you just do this? And it's like somebody else when you're coding. Well, that's kind of what we do for a business, right? So we open the code and we start cursing. In fact, the other day I saw a guy who was so angry looking at a piece of code. He was saying all bad things until he realized it was his code. He just don't remember it, right? Oh, it doesn't feel as bad anymore. So we all go through this problem. We don't really like to take any existing code and change it. But writing new code is really awesome. It's very easy. Well, that's exactly what the open close principle says. You want to be able to extend a piece of code, a software, by adding a little bit of code and not changing an existing code. Now, this is a very important principle because what really leads to a problem with this principle? Often there are two things that really fail open close principle, and that is low cohesion and high coupling. In fact, when you think about long methods are the diagonal opposite of good code, because long methods have low cohesion and high coupling when you really want high cohesion and low coupling. Well, open close principle says methods like that are really hard to change, because when you have to extend it, you got to modify the code to extend it. Let's take a look at a quick little example to get a feel for how this would be a case. So for this purpose, I'm going to start with a very little class. Let's say a class called car equals new car. And I'm just creating a little car, and let's say this is 2015 or 16 rather. That's a little car object I'm going to create. So I'll create this car class, very simple. And now that I have this car class, I'm going to say here is a year value, and we can of course store away the year. Let's say create a field for the year and store it. Well, that's great so far, but I'm also going to provide a car engine, and in this case I'll say this is going to be my engine coming in. And what do I do with this engine? I'm going to store this away also as a field, and I will just store it away as an engine field. But what about this car engine? We definitely need that. I'm going to create a car engine class, and I don't want a whole lot of stuff in this class right now. So all I'm going to do is provide the toString method, and all that this is going to do is simply say return, let's say a get class, and I can provide the name of the class or details of the class. That's more than enough for us to deal with at this time. Okay, great. So that I got some initial code, working for us. What am I going to do with this code? Well, in this case, of course, I'm going to say new car engine. So let's go ahead and create this object, and we can output this. So we can say output car1, and we can see that the car1's data is going to come through. But what about the car class itself? Well, let's go ahead and implement the toString here. So the toString method in the car class simply says return. Let's go ahead and return, in this case, the year value, plus let's say we're going to return the engine value as well. So that should be more than adequate for our purpose. Well, now that we have all this code working, let's go ahead and quickly run this. And you can see from the output that in this case, you can see that the car object, let me go ahead and change the font size here real quick. So you can see that the car object is going to display the details for us. And you can see right there is the car with the details. But I want to really make a copy of the car. So I'm going to say car2 equals new car, and I'm going to say car1, and I'm going to output the car2 in here. Well, the compiler complains that I can't make a copy with this. Why not? Because Java doesn't support a copy constructor. Well, we can quickly fix it. We can say create me a copy constructor for me, please, and we can say other, and within this I can say year, okay, equal to, and in this case I'm going to simply say other dot year value. But what about the engine? Well, we cannot say engine equals other dot engine. That would be considered collision, not copying. So what can we do? We need to obviously make a copy of it. So very benign, I can say new car engine, and in this case we could simply say this is going to be other dot engine, so we can specify the other and then bring in the engine object and make a copy of it. Well, this obviously ripples through. So in the car engine class itself, I'm going to go in and provide a constructor right here, and the constructor that I want to provide is going to be the car constructor, but I'm also going to provide, in this case, well, a copy constructor. So car, let's say engine, and in this case I'm going to say car engine other, and of course not a whole lot to do in this case, but that's good enough for now. Well, let's say in this case I'm going to just leave it alone for now. Okay, great. Now that we have all these code done, let's go back and run this code to see what it does. And looks like everything is what we want, maybe a little bit more. Let's ask a few details about the car and the engine. So let's go to the engine for a minute. And in the engine, let's ask it to give us one more piece of detail. So let's say, give me the hash code. Well, we know one thing for sure. If the hash code is different, we know the objects are different. But if the hash code is same, we can't tell anything. But that's good, the hash code is different. So everything works fine so far. So are we done? Everything seems to work. Are we happy? Well, let's say a couple of months goes by. And now we are told at this time to go ahead and extend the hierarchy of classes. So we are told, in addition to the car engine, we're going to have what is called a turbo engine. But what is a turbo engine? Well, a turbo engine is going to be a class we're going to implement, and this class turbo engine actually extends from a car engine. So we have the constructor, we also have the copy constructor for the turbo engine. So we have implemented those two, so turbo engine, and so that's done. That's awesome so far. So now that we have a turbo engine on our hand, actually I should refactor this. So turbo engine. So that's basically the class we have written so far. So that's quite happy. Well, but the problem in this case is we definitely, let's go ahead and make that a turbo engine. So refactor, where's that? So rename the file. There we go. So that's great so far. But the question is, when we have a turbo engine, where turbo engine inherits from car engine, can we send a turbo engine to the car class? What do you think? The compiler says, sure, go right ahead, right? But when I run the code, notice though what just happened. We got a turbo engine on the first one, but we have a car engine on the second one. Now, why is this really broken? Well, it turns out the reason for that is the fallacy of the new. It turns out that new is not polymorphic in language like Java. If you look at language like Ruby, new actually is polymorphic. So in language like Ruby, you would say a class name .new to create an object. Whereas in language like Java, though, new is not polymorphic. And so the entire slew of factory pattern came about because new is not polymorphic. So it's a sign of a language. The more patterns you see in a language reflects a more of a deficiency in the language itself. And that is what we've been dealing with quite a bit. So how do I fix this? I can come up with a brilliant idea to fix it. What I'm going to do is I'm going to say if other, so other dot, in this case of course, engine is an instance, so instance of, and I'm going to say turbo engine, then I'm going to say engine is equal to new turbo engine, and of course I'm going to take the other dot engine and I'm going to cast that into a turbo engine. So this is going to become a turbo engine after all, so turbo engine. And then of course if it is a else, I'm going to simply make a copy of the engine itself. Well, let's go ahead and try that. If I run that code this time, you can see that in this case it is turbo engine properly on both sides. So the question is, what do you think of this idea? You like it? No, you always have to have a positive attitude in life. This is job security, right? Because we can be maintaining this hierarchy forever and keep billing the clients. So the point really is, this is really sad. But how do we really work around it? Well, it turns out that clone has a problem in Java. If you're curious what the problem is, look at effective Java. They talk about it. So to get around it, we want to use polymorphism. So remember, new is not polymorphic. So we are working around that particular problem. That's all we are doing. So what do we do to get around that problem? So what we are going to say here is engine is equal to other.engine.copy, and I'm going to just make a copy of that particular object. Now this requires, of course, a copy function, which we're going to implement a create a method called copy in the car constructor, in the car class or engine class. And what am I going to do here? I'm going to turn around and simply say new car engine, and I'm going to specify a this and make the copy constructor a protected function. Likewise, if I were to go to the turbo engine class, I can do the same thing. I can implement the copy function right here, and within this, of course, we can say, well, I want to return a new turbo engine of this, and we can turn around. Well, in that case, if you notice, if I go back and run this code, we can keep on adding more hierarchy of classes. We wouldn't have a problem. Just to entertain this thought, let's say we have a piston engine written over here, and this time, of course, I'm going to create a piston engine, and the piston engine is going to be inheriting from a car engine, and we have, of course, our car constructor. We, of course, have a copy constructor, but we also have, in this case, a copy function where we say return new piston engine. And so all we are doing is bootstrapping this to provide polymorphism for construction, which was lacking otherwise. So now if I go back and run the code without having to change the car class, we have the code behaving as we would expect. So the moral of the story is this: we don't want our code to really be affected. We want to add little small modules of code and be able to extend it. So one of the things I would normally ask people is, when I'm doing design reviews and code reviews, is if this code depends on this other code, how hard is it to extend this piece of code? And so oftentimes our vocabulary in talking is, if you do go with this design, you'll be violating the open close principle. And once developers are comfortable with these terms, they immediately clicks and say, of course I'm violating open close principle here, I need to rework this, and they then work through the design properly. But the next principle I'm going to talk about is somewhat related to open close principle, but gets a little bit more specific. This is called the Liskov substitution principle. I'm going to give a few examples of this principle, some good ones and some really bad ones as well. So let's talk about what LSP or Liskov substitution principle says. This principle is all about inheritance. Inheritance is one of the most misused concepts in object-oriented programming. And I'm sure you have all read about this and you said, I would rather not use inheritance, I should use delegation because that's a lot better. Now, why is inheritance not such a great idea? Well, the reason is when you use inheritance, a class takes on the behavior of another class but carries over the implementation as well. And when you do this, it really leads to problems of substitutability. In other words, let's say we have a class A and you have a class B which extends from A, and whether you like it or not, this leads to one small side effect, and that is when you use this, anywhere an object of A can be used, an object of B can be used as well. Now you don't have a way to stop this. So the question is, if B inherits from A, anywhere I use an object of A, I can pass an object of B. But did you really mean to pass an object of B? You have no control over it, you cannot limit it, you cannot restrict it. So in other words, should I, so it's the question is, should I use inheritance? And the answer to that question simply is this. Do you want to use an object of a class anywhere an object of the other class is used? Then use inheritance. If you want to use an object of a class, so let's say in the implementation, right, implementation of the other class, then use delegation. So then the question of course is, why should I not use inheritance? Why can't I just get away with using inheritance? And the reason is, Liskow's substitution principle says, use inheritance only for substitutability. So in other words, you should only use inheritance if your intention is to substitute an object of one class in place of another. Now again the question is, why should I not use it? And let's go a little deeper into this to see why this is problematic. Well, the problem is, if I were to use delegation, so I'm interested in using delegation, so I'm going to say class B, and within this I'm going to say private A and use an object of this. Well, here's the good news. When I do this, I don't have a burden on my shoulder. I am just a user of object A. I have no other responsibility whatsoever. However, if I were to say in this case, a class B extends from the class A, well, whether I like it or not, I am taking on more responsibility right now. What's that responsibility? What you're saying is, if you go this route, you are saying that any external behavior of B is substitutable to the external behavior of A. So in other words, this is a huge burden you're going to carry with you. So what basically substitution principle says is that any services of B should be substitutable, so for services, so in this case for services of B, services of A. Well, again, what does that really mean in English? Well, what it really means is B functions can't require any more and can't promise any less than the corresponding services of the base class. So this is a huge burden for us to carry through when we do inheritance. So your derived class services cannot require more and they cannot promise less than the corresponding methods of the base class. If you're going to use delegation, you're home free. You simply say, I'm going to use this other class, I have nothing to stop me. If you're using inheritance, not only are you developing your class, you got to sit there and say, is this conforming to what the base class expects every step of the way? That's a large burden that we have to carry. Now, books have been written to say, do not use inheritance or use that very sparingly, use delegation most of the time. But here comes the charm. You read the book, it's next to you, and it says, use delegation, not inheritance. And you say, this is awesome, great book by the way. And you put the book down, you turn to Java, and what do? Use inheritance, right? Now why? Because this is called viscosity. Java makes it so much easier to do the wrong thing. Let's take a look at an example of this. Let's say for a minute, you have a class on your hand, a class called A, with the function, let's say, void f1, and doesn't matter what this function actually does, and I have a function f2. And what does this function do? It's returning some result. It doesn't matter really. So this is what you have with you so far. Now you are told to implement the following. You're told implement a class B, and the problem requirement says B should have the same functions f1 and f2 as in A, and a new function f3. That's what you've been given. Now honestly, what do you say? You look at this and say, hey, f3 is cool, so public void f3, you implement whatever you want to do in f3, you get it implemented quickly. And then you look at this other function, f1 and f2, and there's a little temptation, right? And you say, I can get this done and I can go home for dinner. So what I can do is, I can say extends A, and you're like, this is awesome, right? I didn't have to write all that stupid code, it's all done for me. Well, guess what? Now I can take an object of B and send to an object of A, whether you like it or not, and it better be compatible to it. So the question is, what can we do to solve this problem? The first thing is to avoid this temptation. A better solution is not to extend A, and you have to do a little bit more work. You say private over here, A object equals new A, and then you say public, let's say void f1, and within this you say object dot f1, and then you write public int f2, and then you say return object dot f2, and you have to write that code. Now notice the beauty of this. You are delegating to A, but nobody can take an object of B and send it to where an object of A is expected. But there is one small problem. You had to type all that code now. How do you solve that problem? Very easy. If you cannot do it, find somebody else who's really fast in typing. Right? That's one way to solve the problem. Or, this happens to be such a common problem, we find tools to get us out of these mess, isn't it? So if you notice, this is such a common problem, you go to this and write this gently as inheritance, but don't check it in. Turn your computer away from the window so nobody sees you are doing this, and then quietly click on it, and you say refactor, and then you say use inheritance, replace inheritance with delegation, right? And then you click on that very gently, and then you select the methods, and then you let the tool do the stupid job, and you're done, right? So you can do that as well. But even if you want to go this route, we just traded one problem for another set of problem. Well, guess what? We are not violating LSP anymore. But unfortunately, we are violating two other principles. Now, how come we're not violating LSP, but what other two principles are we violating? Well, sadly, we are violating both the dry principle and the open-closed principle. Hey, how so? Let's talk about the dry principle. Notice you had to write this code again. That's a violation of dry. That's a duplication of effort, isn't it? So it's a violation of dry. Even more serious, it's a violation of open-closed principle. How so? If you come tomorrow and change this function signature, your B class is dead in the water. So every change to A will affect a change to B. So now you got stuck between a rock and a hard place. Should I violate LSP or should I violate dry and OCP? The short answer is I would rather violate OCP and dry and not violate LSP. Why? If I violate LSP, I affect the user of my class. If I violate the OCP, I take the burden and maintainability. That's better. But ideally, of course, it would be nice if you don't have to violate any one of those principles, wouldn't it be? Yes, you can, but for that you have to momentarily leave Java. Let's see how we can do this. I'm back here in Groovy, and we'll see what Groovy does to solve this particular problem. And oh, by the way, there's a project called Open Lumbuk, I think. They actually implement this in Java as well. So you can take a look at Java and the library. You can do something similar to this in Java also. But I'll show you how you can do this in Groovy. I got a class called worker. And the worker class has a function called work. And what does the worker function or work function do? Print line, and it says working. So you can see that's the worker. Let's give it a try real quickly. Joe equals new worker, and joe.work and call the work method, and you can see that it actually is working. But we're not interested in the worker. We want to move a little forward. Let's say we have a class called manager. As you would expect, manager does absolutely nothing. So I'm going to say Bob equals new manager right here. And in this case, I'm going to say Bob.work. But this manager is really awesome, very smart. And the manager says, oh, you want me to work. Now, this is an alien concept for most managers, but not for this Bob. So this Bob says, no worries, and simply says worker, victim equals new worker, and simply says delegate over here, and you can see how nicely that actually works. So this is a very powerful way of doing this. So what did just happen? Well, notice this code follows Liskov substitution principle. It follows open close principle and follows the dry principle also. How so? Well, it's the compiler doing the job for us rather than an IDE vomits doing the job for us, right? So essentially what's happening in this case is the compiler comes around and says, aha, you are writing a manager, but you're delegating that to the worker, and at compile time, it synthesizes the function that you and I would have written using hand or using the tool to generate the code. But the beauty of this is, tomorrow if you decide to change this work to some other function, right? So for example, get work, do work, let's say do work instead of work, notice I did not touch the manager at all. I simply call the do work method and everything works just fine. But this is even better because this is very smartly done. For example, the question is, what if the manager has a method already? So let's give it a try. Let's go to the worker class and we will write a method called vacation. Now you all know what vacation feels like, right? Print line, a code, so code on the beach, right? So that's what we do when we do a vacationing. We take the code with us, right? We're some bunch of sick people. But that's what we do, at least that's what others think. But we know we're having real fun with it. But what about the manager? The manager is, of course, not going to be relenting on that. So vacation is a function, and this one says year long, right? So there's a year long vacation managers usually have. So I say Bob.vacation, and of course what do you expect? The manager is not going to let the worker have the vacation, and so you can see that it actually handles this very, very well. So this is an example of how code can be compliant to Liskov substitution principle as well, but we have to always think about substitutability quite often. The last principle I want to talk about here, I'm going to actually talk about this without even writing a code, but giving you an example of this. So let's switch over to a little example of what we can do with this. So I have a person class, and let's start with this first. Well, this reminds me of my very, very first visit to Norway. This was a good day, I'm going to say about 16 years ago. Well, if you remember the time 16 years ago, we didn't have cell phones and smartphones like we do now. Laptops were new back then. So I go to Norway quite often these days, but back then that was my first trip. I go to the hotel and I check in, and I realized that the Norwegian hotels don't give coffee makers in hotel rooms. And I was a bit shocked because the hotels here, they always give you a bag coffee and coffee maker, but they didn't have any over there. I went to the reception and said, excuse me, I don't see a coffee maker. They said, we don't give you coffee makers. And I argued enough that finally the lady at the front desk said, you can take my coffee maker. She wanted to get rid of me. So now I have a wonderful coffee maker with me. Well, it was about time to go to bed. And I'm a guy who usually goes to bed early and gets up early. So I'm ready to go to bed. I look around the room, and I was a bit shocked because the room did not have a clock. And it bothered me. I said to myself, what's the matter with this Norwegian hotels? Maybe they don't give you anything that starts with a C. No coffee maker, no clock. So I went down to the reception. The lady was not too happy to see me. She said, what is it now? I said, there's no clock in my room. And she said, that's correct, we don't give clocks. I said, well, I got a problem now. How do I wake up in the morning if there is no clock? And she looked very confused. She said, why would you need a clock to wake up in the morning? I said, you see, by my bedside I have this clock, and early in the morning it makes such a horrible noise, I cannot sleep for the rest of the day. I want something like that to wake me up. She said, oh, you need an alarm, not a clock. I stared at it for a minute and said, don't get technical on me, lady, right? And I thought about this for a minute and said, she's actually right. I don't need a clock, I need an alarm. I said, okay, well, that's fine, but I don't see a clock in my room. She said, you don't need a clock in your room. Well, fine, I don't see an alarm in my room. She said, did you turn on the TV? I said, no, of course not. I don't watch TV. Well, this week you will. So I went back to my room, turned on the TV, and what a surprise. And the TV said, welcome to the hotel. This is your alarm too. And I was really fascinated by this. It's great to turn on the TV once in a while. Technology kind of changes. This had an alarm in it. Can you believe it? So, but I'm a big fan of TDD. I'm not going to believe it. So I set the alarm for 2 minutes from then. I turned it off and I kind of waited for 2 minutes. And 2 minutes later, ta-da, it turns on. Of course, I'm not going to believe it. Set it for 5 more minutes, go brush and come back, and it turns on in 5 minutes. But I noticed a bit of an anomaly, though I got to agree with that. No matter which channel I set it on, not that it matters to me, but you know how testers are, right? So no matter what channel I set it on, it would always turn on CNN. So anyway, I thought, I'm still debating, is it a bug or a feature? But anyway, I kind of set the alarm for 4 a.m. and I went to bed. And I usually sleep like a rock, not a problem. So I'm sleeping, and you can't imagine this only. Now I'm in a dark room in a foreign country, not knowing where I am. And suddenly at 4 o'clock, I hear a voice. And I'm in a panic right now because I'm not supposed to hear a voice where I'm supposed to be alone in a room. I get up and look over, and I saw the scariest scene anybody could ever see. Because the TV was on. I don't even watch TV, but it's on. And on the TV, there's this guy in suspenders. Hello, this is Larry King Live. I'm like, what? And can you ever imagine waking up to Larry King Live? I had to go to counseling after I came here. But anyways, now that I was awake and turned off the TV, I thought about it, and I realized something. This lady taught me a lesson, and that is, she said, a person should not depend on the clock. A person should instead depend on an alarm. Well, think about that for a minute. If a person depends on a clock, that is tight coupling. And in this case, though, we're saying person depends on the alarm. What's the benefit? Well, that particular week, I had the TV for the first day. And of course, my TV is actually an implementation of the alarm as well. Nowhere, no other conference will you see UML diagram being done on a notepad. So there you go. So you can see that in this case, we have this inheritance hierarchy where you have the alarm being implemented by the TV, as you can see right there. Well, that's great. But then, of course, quickly realize there are other things. My wonderful clock at home also is an implementation of my alarm. And the beauty is I could use the TV as an alarm, but I can also switch over to a clock as an alarm if I wanted to. And later that week I decided I really need something a lot better than that. So I decided to reprogram my computer so it would blare and wake me up. My computer could be an alarm. These days, of course, my phone could be an alarm, but I do have to agree that the alarm that I love the most, undeniably for myself, is, of course, my wife. And she is the best alarm for me because, undeniably, that wakes me up every time. So the point is, spouses can be a great alarm. So this could be a spouse depending on whom you're waking up. So spouses could be an alarm as well. And the point really is you can start designing your system where you can have various different implementations, but you can substitute for the original. Well, therein is the so-called dependency inversion principle. So what does a dependency inversion principle say? It says a concrete class like person should not depend on a concrete class like clock. Instead, both the concrete classes should depend on an abstraction. So in other words, rather than a concrete depending on a concrete, both the concrete now depend on abstraction. That's where the dependency inversion comes in. If you use automated testing and you do mocking, you automatically use dependency injection principle. So I find these two principles, open, closed, and DIP, to be very fascinating because oftentimes I try not to violate the dependency in open-close principle, but oftentimes I end up using the a principle of dependency inversion principle as a kind of antidote for that. Well, I did promise to you though, I will give you some examples of this. So anytime you use a mocking object, or anytime you want to support automated testing, the chances are you very heavily use dependency injection principle. Not only that, you also use dependency inversion principle anytime you want to be able to substitute different implementations. For example, you want to have a parser, but you don't want to tie to that specific parser. You may go through an interface and swap between multiple different parsers. Or when you use the strategy pattern, one algorithm gives you a faster convergence. Another algorithm gives you better accuracy. And you want to be able to switch between one versus the other depending on what you're doing. What design principle does the strategy pattern use? Dependency inversion principle. This is one of the reasons why when I teach design patterns to teams of developers, I never teach design patterns first. I always teach design principles. And then when I take on every single design pattern, I always ask, what is the force behind it? What's the underlying design principle behind it? And then we end up really talking about how this pattern actually evolves based on this principle. For example, if you think about the iterator pattern or the composite pattern, these are really good examples to think about. Iterator pattern fundamentally uses the dependency inversion principle. The composite pattern, on the other hand, is really after the Liskov substitution principle. So there are these nice things about these principles. But talking about Liskov substitution principle itself, there are times when you can see good uses of this, and there are times you can see really bad uses of this also. Let's look at an example of a good use versus a bad use for a minute. Now, a good use of this pattern, let's say you have a class called A on your hand, and you're going to extend from this, and you're going to extend a class, B from it. Now, I'm going to say in here, protected void f1, and notice that the compiler immediately gives you an error. It does not permit you to make the method f1 protected. Why is that? That's Liskov substitution principle right there. So it says if you inherit and make this more restrictive, you are going to run into trouble with overriding. It doesn't want you to do this. This is a good example, as you can see. Likewise, if you were to take this function, but suddenly you want to say throws IO exception, for example. Well, the compiler again complains. Why? Because if you decide to throw a new exception, the user of the class A is going to be in trouble. Because the user of class A says, I'm going to call this method and I'm not expecting any exceptions from it. You create an object of B, pass to the method, and suddenly it blows up. It's not going to be really happy with it, right? This worked fine until yesterday. What happened to this? And now you're going to say, oh, so I got to ask, it's a base class or derived class. If it's a base, I don't need a try catch. If it's a derived, I got to put a try catch. Well, what will happen? You end up violating the open-close principle. Then anytime you violate Liskov substitution principle, invariably violate the open-closed principle as well. So that is the reason why Java says you shouldn't do this. Java doesn't go far enough in that it doesn't come back and say, well, you got a base exception on the top, and here you have a derived exception, and Java says that's okay, but in reality, it really is not, so you have to think a little bit further with it. Again, these are good examples. But I'll also give you one bad example as well. And what is the bad example? Well, the bad example is, let's think about the class called stack. Well, stack class in Java, what does that do? Well, let's take a look at the stack for a minute. We know what a stack is. A stack is a LIFO, last in, first out. And that's the only thing you're supposed to do with the stack, right? You put stuff on the top, you remove the stuff from the top. That's all you're supposed to do. But unfortunately, though, if you look at the stack class, notice what they have. It inherits from a vector. Now, what can a vector do? You can insert elements anywhere in a vector. You can remove elements anywhere from a vector. What's the consequence? Imagine this for a minute. Let's say she has a function which is going to receive a vector. and she passes that to him, his function. What does his function do? Uses a vector. He then passes that to the third function, and his function, what does it do? It takes a vector and says, hey vector, and he inserts elements and removes elements. I come along, I create an object of stack, and I send it to her. What does she say? Hey, nice vector, and passes it down to him, and that further down to his function. And now I get back my stack, and the stack says, please don't do this to me again, right? And the stack is limping through and says, I completely violated, right? So the point really is we violated the invariant of the object. So one of the contracts of objects is invariance. What is an invariance stack? Invariant of a stack is you always put stuff on the top of the stack and remove from the top of the stack, and you never alter the sequence of elements in between. Well, when you treat a stack as a vector, you completely violate the invariant of a stack, and that's not fun at all. That is an example of a very poor from the point of view of the Liskov substitution principle, and we have to be very careful about this. So in summary, we talked about a few very useful design principles. These principles have been around for a while, but I keep using that almost every single day, especially during test-driven development. And these principles have been very valuable to create better quality software that is easier to change, easier to evolve, easier to maintain. It really helps us to think through about cohesion. It helps us to think through about coupling. It helps us to think through about maintainability of code and evolution of software as well. And overall, I found this to be extremely beneficial. And using these principles also has been very powerful from the point of view of using them as a vocabulary when communicating with teams as well, and that's been very helpful. So I've really gotten good mileage out of these principles. I sincerely hope you will too. I hope you found this useful. That's all I have. Thank you.